CTs and PTs, that would be instrument transformers if you group them together. And we're going to look at how they're built and how to apply them. These are This is the equipment that is going to connect a high voltage system to the meters and relays that we use to work with the system. So it's a safe way to link high voltage with essentially low voltage equipment. So CTs are really pretty simple. Here's some different varieties of them. This one is what we might call a donut CT. Essentially, you take the large power conductor, it goes right through the middle of the hole here. This CT, of course, the wire is cut and attached to each end here. So the primary goes through the inside of this CT and then out, and the secondaries of the CT are connected right here. And then here's a high voltage one. This is basically the insulator, if you will, and then the CT goes through the top there. So what are they? Well, it's an air core transformer with few primary turns, usually one primary turn. The primary turn is the conductor that you've inserted through the middle of it. And we usually see these rated 50 to 5, 100 to 5, 200 to 5, that sort of thing, 400 to 5. Now, if you look at that, the ratio means really it's a 10. This would be a 10 to 1 transformer, and this would be a 40 to 1 transformer would be. But we use this to 5, and that's based on the old panel board meters being rated 0 to 5 amps. There's basically two different types. There's relaying CTs and metering CTs. Relaying CTs aren't quite so accurate, but they maintain a reasonable accuracy with a lot of current going through them. So during a fault situation, they still work reasonably well. In other words, they saturate at high currents. Metering CTs, they're more accurate because you're buying and selling power. However, during a fault situation, they're not quite as useful. So they're different designs, metering and relaying. Now, these CTs, and you'll see with the PTs, they're really not meant to energize things. Like, they're not really meant to drive loads. They're meant for measurements. So we try to limit how much, when we call it burden, how much equipment we put on these things, because we don't want to impact their accuracy too much. So one of the key things to remember with CTs is that an open CT can be dangerous. A shorted CT is a safe CT. And that is just the opposite of what we're used to compared to voltage transformers. So here's a little picture of a kind of a mock-up of a CT. Here would be the main power going through the middle, and we call that the primary winding. And then the secondary is really just these wraps around this core. And you'd have to go around and count those, but there might be, let's say that's 20 wraps. Well, then that would be 100 to 5 CT. If we have 100 amps flowing through the primary, we'll get 5 amps on the secondary. So here's a representation of it schematically, a CT, right? You got the little bubble deal, that's the schematic. And notice this already has a shorting switch built in, so we can short this CT and leave it shorted for safety. If we open that switch, now current will flow through, in this case, an amp meter. So that's a nice little depiction of a transformer. Again, the primary, notice this even says H1, the primary, the cable would go through the middle. That's the primary, one turn if you will. And then the secondary are the wraps around the outside that come out X1 and X2. And this would go to your device, a relay or a meter, that sort of thing. Here's another look of a similar kind of window CT, or sometimes I think they sometimes call them donut CTs, or a bagel CT, or a Cheerio CT. We could call it all kinds of things. Now, the bar type it's the same principle, but here's the conductor passing through, and you're just connecting the conductor with a NEMA connector, a 2-hole connector on either side. But again, it's the same principle, primary through the middle, and then the secondary going on the outside here. So we're going to use these in relaying and in metering, and you're going to use them in the labs. In the lab, it's a little goofy because in the lab we actually increase the current instead of decreasing it. Now this is showing both a potential transformer and a current transformer to this system, because a watt meter needs both voltage and current. But remember, there's the symbol for a current transformer. Potential transformers are really they're just transformers that like we're used to. The only difference is they're high accuracy, and they're really not meant to run lights and motors and things. They're meant just for measurement and for relaying. So that's what we're talking about here, a voltage transformer, which is really, we call a PT, potential transformer. And they're just very accurate small transformers, and they're really not used for loads. So here's an example of a voltage transformer, but it's very precise. That's the idea, is that you have a very good, if we start with 7200 volts up here, and down here we have 120. Now 120 is something we can put into a meter or relay quite easily. 7200 volts would be a little scary. So now here this looks like guts on a fence, but this would be an installation. This was taken kind of out near Rosette, where CTs and PTs are installed together, and with no regard for making this look good. And if you look really, really close, you can kind of figure out what's what. But this is a potential transformer, and so is this, and so is this. If you look really close, the potential transformers are 120 to 1. Now these are the CTs, and they look like they're 200 to 5. This was done on what we call a primary metered service. So the customer was taking power at a high voltage. I don't really remember what it was. I think it was maybe 24.9 kV, and we were using these devices to measure the power that they were taking, so they could be billed and make money. All right, so here's a few questions for you. You got a secondary current on a what's the secondary current on a 400 to 5 CT? Now that's a ratio of 80, right? 400 to 5 is a ratio of 80. If there's 150 amps on the primary, well, hey, if there's 150 amps on the primary, just divide that by 80, and you will quickly determine that it is 1.88 amps, right? I mean, if I had 400 amps, I'd have 5 on the secondary. If I had 200 amps, I'd have 2.5, right? If I had, so you know it's going to be less than 2. So anyway, I got 1.9 and roughly. Okay, let's skip that one. When working on a CT circuit, it should be what to protect the worker? If you're going to work on a CT circuit, you short the CT circuit. Let's say you have a CT that's rated at 200 to 5. It has a TRF of 2. TRF is transformer factor. So a 200 to 5 CT really could, that's the ratio, but that doesn't really tell you, that alone doesn't tell you how many amps it's rated for. And so stamped on the CT will sometimes have something called a transformer factor, which means if you had 2, then this really is, this transformer, this CT would be rated at 400 amps on the primary and 10 amps on the secondary. And it's all temperature based. They'll in fact even stamp a temperature on there. So that's what that dude would be rated for. Okay. CT circuit loads are connected in series. They're connected in series, while PT circuits are connected in parallel. So the CTs are really a lot different than voltage transformers. You connect the loads in series instead of parallel. You short them instead of opening them. And they maintain a steady current, not a steady voltage. So, and then some different styles. Hey, we looked at window type, and we looked at bar type, and we looked at bagel type. There's all kinds of different configurations.